Okay, this is lecture 19. It's about the switching lemma, in particular Hostad's switching lemma, which I have stated here. So the theorem of Hostad says, let's say we have some DNF or some CNF phi of width at most w. So that means if it's a DNF, that every term has at most w literals in it. Then for every parameter h, a natural number, we have the following. So suppose we choose a random restriction rho with star probability epsilon. So each coordinate is star with probability epsilon, and is otherwise 0 or 1. It's fixed to 0 or 1 with probability half each. And now we look at phi restricted by rho. And we ask ourselves, what's the best height of a decision tree computing that restricted DNF? Well, the probability that it still requires a decision tree of height at least h is very small. It's exponentially small in h, where the base of the exponent is a constant times epsilon times w, the width. Okay, and what's amazing about this switching lemma of Hostad, it has absolutely no dependence on the size of the DNF or the CNF, just on the width. Now, there are two known proofs, essentially, of the switching lemma. The first proof is Hostad's original proof. And this is a rather amazing proof. It's by induction on the number of terms in the DNF. And as soon as you start, doing the proof and, doing induction on the number of terms, you start to get into a lot of conditioning. And the amazing thing about his proof is that you just incredibly strongly strengthen the induction hypothesis so that it can handle almost an arbitrary amount of conditioning. And amazingly, the proof still goes through. The second proof of the switching lemma is due to Razborov. So it was done subsequently to Hostad's proof, and it was appeared in a paper called a switching lemma primer by Beam, and most people refer to that when they refer to Razborov's proof. And in some sense, Razborov's proof is the same as Hostad's proof, but really written in a different way. In particular, it's got sort of an amazing structure that I've seen hardly anywhere else. It proves that some probability is small by taking all the bad outcomes for the restriction and somehow encoding each bad outcome by some kind of other object and then counting the number of bad other object encodings and showing that it's small. So it's kind of an amazing proof strategy as well. And Razborov's proof is the one that's always sort of given, in lectures or in classes or in books. So, for example, Razborov's proof is given in the textbook, Aurora Baroque, and I'll also put up on the course webpage a PDF I wrote from the last time I taught complexity giving Razborov's proof. But actually, today in this lecture, I would like to give Hostad's original proof because, well, it's very rarely given, and it's not actually harder than Razborov's proof, just different. So I would like to show that to you in this lecture. So let me erase this one. Now, before I get into that, it is still a somewhat difficult proof. So before I get to it, I want to do a different proof, an easier but weaker proof. Okay, so this easier but weaker result, version of the switching lemma, is due to Patassi, Rossman, Servideo, and Tan, and it's just from about a year ago. So they were doing some coding theory proof complexity result, and they needed some kind of more complicated version of the switching lemma, and in the their setting was already complicated enough, and they decided that the original proof and Razborov's proof of the switching lemma were too complicated to handle their more complicated scenario. So they invented this simpler and more flexible, albeit quantitatively weaker version of the switching lemma, and that's what I'll show you first in this lecture. And it's quantitatively weaker because instead of 5 epsilon w to the h, it gets basically 2 to the w in place of w. So it actually has order epsilon w 2 to the w to the h. Okay, so that's quite notably less good, but as I said, the proof is much easier. And given this, you can get corollaries for things like parity not computable by constant depth circuits of polynomial size. If you just follow through the parameters, it's not too hard to show that parity n requires depth d circuits of size n to the omega of log n over d squared. Okay, so for any constant d, it shows that parity requires circuits of super polynomial size, n to the log n. That's much worse than Hostad's 2 to the n to the 1 over d minus 1. But it's still decent in the sense that it gives you a super polynomial depth bound even for d almost as large as square root log n, which is pretty good. Hostad's gives it to you for depths almost as large as log n, but up to square root log n is pretty good. But in fact, even before I get to this proof, I want to just give you a really simple proof of some kind of switching lemma. I'll call this the warm-up for PRST. And this is a switching lemma that has parameters pretty much like the Hostad switching lemma, but instead of being about switching CNFs and DNFs down to decision trees, it's simply about switching decision trees down to decision trees. So it's quite a bit easier, but it has a much, much easier proof. And it's a good warm-up for the somewhat easier switching lemma of Patasi et al. Finally, I should mention that if you only care about getting the best result, Hostad's switching lemma, it doesn't need any of this PRST or the warm-up at all. So if you really just want the top quantitative parameters, you can skip these warm-ups that I'm going to do. But we'll do them because they're a little bit easier. So I'm going to do these things in reverse order. I'm going to start with the warm-up, and then do the PRST switching lemma, and finally I'll do Hostad's original proof of his switching lemma. Okay, so we're going to start with the warm-up. So as I mentioned, the warm-up is similar to Hostad's switching lemma that takes DNFs to shallow decision trees, but it simply takes decision trees to shallow decision trees. So let me write this warm-up theorem that we're going to prove. So the warm-up theorem says the following. Let phi be a decision tree of depth at most w. Okay, so any such decision tree of depth at most w is also a DNF and a CNF of depth, sorry, of width at most w. But decision trees are a more special case. Okay, then for all parameters h, as before, in the natural numbers, the probability, if you choose a random restriction with star probability epsilon, that the decision tree depth of phi restricted by rho, the probability of that being at least h, is at most 2 epsilon w to the power of h. Okay, so we can compare this with Hostad's switching lemma. It had 5 epsilon w to the power of h, which is a bit worse, but it's for a much stronger situation when you start with a DNF. In fact, not that this really helps much with anything, but we can even make this a little bit better. We can add over h factorial here, which I suppose is good if h is pretty big. Okay, so this is what we're going to try to prove. We're going to try to show that a decision tree of depth at most w really gets crushed down to a decision tree of depth less than h, except with exponentially small probability when you hit it with a random restriction. Okay, so let's prove this. And let's start by looking at the event that we're concerned with, that the decision tree depth of phi when restricted by rho is at least h. Okay, so we hit it with rho, and the decision tree still has depth at least h. Well, I'm going to make a very simple observation. If this happens, still the restricted decision tree has depth at least h, then if you take a random path down this decision tree, there's a slight chance that you'll take a path of length at least h. then the probability that if I take a random path P down the decision tree, it's not a nice P, the restricted decision tree, the probability that the length of this path is at least h is at least 2 to the minus h. And let me just draw you a quick picture to illustrate that. Suppose the restricted decision tree looked like this: x3, 0, 1, x2, 0, 1, x1, x4, 1, 0. Okay, I haven't fully drawn it here, but this is part of the decision tree. And this has depth at least 3. And if I take a random path, that really just means you start at the roots and you go left and right with probability half each. Well, if there is a path in here of depth h, you have a 2 to the minus h chance of ending on it. Okay, in a random walk down a decision tree, the probability that you get to a leaf at depth h is exactly 2 to the minus h. Okay, so that's a very simple observation. Let me erase my picture here and proceed with the proof. Okay, so we're going to rely on this fact that if the restricted decision tree has a leaf at depth h, then a random path in that restricted decision tree will at least occasionally hit it. Okay, so what we can conclude is that the probability that we're seeking up here, that when we pick a random restriction, this event happens, is at most the probability of this even more likely event happening. What is this even more likely event happening? It's the event that when you pick a random path, P, in the restricted decision tree, you get down to depth h. Okay, so this is a somewhat funny observation, but quite simple. Now let's proceed. Let's look at this probability. It's the probability of some weird thing. Just for a second, think of this as just some weird random variable, x. The probability that x is at least 2 to the minus h. Okay, we can upper bound this using Markov's inequality. The probability that x is at least 2 to the minus h is at most the expectation of x divided by 2 to the minus h. Okay, so let me clean this up a little bit. So divided by 2 to the minus h is the same as times 2 to the h. And the expectation of x, well, let me just remember what x is. It's this strange probability here. So let me clean this up. It's 2 to the h times the expectation over rho, a random restriction, of this probability. The probability when P is a path in the restricted decision tree. Okay, let me clean things up here. That the length of P is at least h. Okay, that was Markov. Okay, time for the next step. Okay, now the next step is a bit of an interesting step. Well, just before we get to that step, let me combine the expectation with the probability. The expectation of the probability is just the probability of everything put together. So rho, a random restriction, and then P, a random path in the restricted decision tree of the length of P being at least h. Okay, so the next step is this interesting step. So let's take a look at this somewhat complicated experiment we're doing here. We have a decision tree, phi. Let me imagine it here for a second. This is a hypothetical start to a decision tree phi. What are we doing? First, we're choosing a random restriction rho with star probability epsilon. We're restricting the tree according to that distribution, and then we're choosing a path P in the restricted tree. Now, I claim there's another way to look at this experiment, and let me talk you through it. So let's say we have this decision tree, phi, which I haven't fully drawn. And first we're going to imagine choosing a random restriction where we set each variable to star with probability epsilon, and the unset variables we fix them to be 0 or 1 with probability 50% each. And first of all, let's imagine choosing this random restriction in a kind of lazy fashion, or a fashion that's sort of decision tree directed. So what do I mean by that? Here's how I'm going to imagine choosing the random restriction and at the same time restricting the decision tree by that random restriction. I'm going to kind of do it lazily. So first I'm going to go to x1 in the tree. And now's the point I'm going to ask, okay, in row, how is x1 set? And let's imagine that in the random restriction, x1 gets set to star. Okay, so I'll write that here. Let's say x1 gets set to star. Now, what does that mean for the restricted decision tree? It means nothing. It means that x1 sticks around, it's unset, and this remains part of the restricted decision tree, phi restricted by row. Now, in the second part of this experiment, we're choosing a random path in the restricted tree. So the restricted tree still starts with x1, so we choose a random path. We either go left or right with probability 50% each. So let's imagine that we go, I don't know, right. So this is going to be P in the restricted tree. So let's say P sets x1 to be 1. Okay, so then we come down here to x2. Now we go back and think about how x2 is set in the random restriction. Again, it's set to star with probability epsilon and 0, 1 otherwise. And let's imagine, that it's set to 0. Okay, so that's quite possible. Say that it's set to 0. Okay, and what effect does that have on the restricted decision tree? Well, it's really as though, let me just draw a little bit more of it here. It's really as though you would just short circuit this piece. So in the restricted decision tree, when you restrict x2 to be 0, you would just sort of short circuit this wire up here, or this path up here. Okay, let me erase that though for cleanliness. Sorry, I wrote star over here. I meant to write 0. That's a little confusing. Okay, so when we come to looking at the path P, we don't have to do anything for x2 because under the restriction, x2 is fixed to 0, so there is no, choice for x2 in the restricted tree. Okay, so let's proceed. We're still, we're now at x4, and we're imagining what x4 does in the random restriction. Notice that we're picking the random restrictions, outcomes in a peculiar order, but that's okay. We're just always going to do the correct thing when we see a variable, set it to star with probability epsilon, or 0, 1 with 50% each otherwise, even though we're doing it in an odd order. That's fine. So let's say the random restriction chooses to make x4 star. Okay, that happens with probability epsilon. Okay, so the restricted tree, x4 still is alive. Remember, the restricted tree really looks like this now, because x2 was set to 0. But anyway, x4 got set to star. So now, when we're choosing a path P in the restricted tree, we do have to make a choice for x4. So perhaps we choose 1. Okay, so now that means the path took us to here. We're at x3. And, we keep going. So we ask, okay, how does the restriction set x3? Perhaps it sets it to, I don't know, 1. Okay, so then imagine that the original tree, it looked like this. Okay, and then in the restricted tree, x3 has been set to 1, so this kind of becomes a short circuit. And the path doesn't even have to make a choice about x3, so never mind. Okay, and we're at x10. Okay, and again, we can continue making choices for the random restriction. And whenever we get a star, kind of doing them in perfect alternation here, but that's the clearest way to make the point, the path also has to make a choice whether it will be 0 or 1, let's say 0. And this tells us which variable to look at or think about when we're making a random restriction. Okay, and so we keep doing that until we hit a leaf. And at this point, we can kind of actually stop with the experiment. I mean, we can imagine that the remaining variables in row, which are like x5, x6, etc., are chosen to be star 0 or 1 with the right probabilities. But we don't actually need to evaluate how this experiment concludes. Okay, so so we've thought about this experiment in a funny way. And now what I claim is that here's an equivalent way to think about this experiment. Let me give myself a little room here. The claim is that we can kind of invert these two aspects of the experiment as follows. So what we can do is, the claim here is that this is the same as, this experiment is the same as taking a random path Q in the original tree, and then replace each assignment in Q with a star with probability epsilon independently. Okay, so what I mean by that, what I mean in this claim is that another way to look at what happened is we're going to start at the root and we're going to take a random path down the tree. I'm drawing the exact same path that we took. And that's going to be Q. And then for each variable that we encountered on the path Q, we'll sort of go back and set it to be a star with probability epsilon each. Okay, I've kind of made this a little bit messy. But I hope you can agree with this claim that this gives us the same distribution on sort of partial assignments Q as it does on P. Okay, so again, Q, I just take a random path down the tree, and then I kind of go back and retrospectively set each variable along that path to be star independently with probability epsilon. Okay, so again, it gives some kind of partial assignment, finally, to all the variables in the path, but minus the ones we retroactively set to star. And I'm claiming that this is the same as the distribution on P. Okay, so I hope you find that claim justified. Okay, so I did a bit of a weird edit there, but hopefully you're still with me. So I hope you agree with this claim that Q and P have effectively the same distribution. What I want to emphasize here, because we're interested in the length of P, is what does that have to do with Q? Well, the length of P in the restricted tree is, in this case it was 3 so far, it was effectively the number of stars in Q. Okay, so this is the last point I want to emphasize, that the length of P in the restricted tree, when we think about it this other way, where we choose a random path Q in the original tree, and then go back and replace each variable with star, the length of P is the same as the number of stars in Q. Okay, so having explained all that, let me go and continue the proof. So by virtue of the claim, what we now have is that this equals 2 to the h times the following. The probability when Q is a random path in the original tree phi, and then stars put into it with probability epsilon each for each variable that gets assigned by Q, the probability that the number of stars put into Q is at least h. Okay, so that's what I've used the claim to justify. Okay, and now you see this is actually much simpler than it looks, because I've picked a random path Q in the original phi, and then I go back and replace some of the variables with stars, and I'm just concerned with what's the probability that the number of stars is at least h. So in fact, this is nothing more than the number of stars in this path Q is nothing more than some binomial random variable. So it's really exactly the probability if I choose Q to be a random path in the original phi. And then I don't, go back and put the stars in, but I just ask, well, what's the probability that were I to do a binomial random variable with length of Q trials and epsilon probability of succeeding, of getting a star, that this would be at least H. Okay, and this is a key point to have reached, so I'll mark it ironically with a star. Okay, and now we're home free. In fact, at this point, I'm simply going to say that since the original tree phi had depth at most w, the length of this random path q in it is at most w, and this probability of the binomial being at least h can only go up if I increase the length of q, this random variable, whatever it was, to its maximum possible value, which is w. So this is at most 2 to the h times, well, simply the probability that a binomial random variable with w trials and epsilon probability of hitting is at least h. Okay, and now we're just at a calculation. So if you have a binomial random variable with w trials, and you're interested what's the probability I get at least h successes, well, you can simply union bound over all h sort of outcomes within the w trials, or positions within the w trials, of the probability of these all being successes, which is simply epsilon to the h. Okay, and now we'll just use the w choose h is at most w to the power of h over h factorial. Okay, and finally this is exactly what we're shooting for, 2 epsilon w to the h, and we can even save this h factorial. And that concludes the proof of the warm-up for the PRST switching lemma. Okay, so that is the warm-up to the PRST switching theorem, and now we'll do the full PRST switching theorem. So let's go back and take a look at the Hostad switching theorem. That's our final main goal. Okay, so remember it says that if you have a DNF or a CNF phi of width at most w, then we have this result about switching when you restrict it with a random restriction with parameter epsilon, star parameter epsilon, the probability you get a decision tree of depth at least h is exponentially small in h, something like 5 times epsilon times w all to the h. And as I said, Pitassier, Rossmann, Servideo, and Tan have an easier analysis, giving a weaker result, where basically instead of constant epsilon w in the exponent, you get constant epsilon w times 2 to the w. So basically epsilon times 2 to the w in the base of the exponent. So let me show you that. And in fact, it actually does it for something even more complicated than a DNF or a CNF of width at most w. And that's part of the reason it gets a correspondingly weaker result. So let me tell you about that. So let's go back down here, and we'll start talking now about the PRST switching lemma. And let's think for a second about what a width w, let's say DNF, looks like. So let's say we had some width w DNF phi. Perhaps it looks like, perhaps 3 is w. Let's say w is 3. And yeah, perhaps phi looks like the following. x1 and x2 and x7 bar, or x3 and x2 bar and x5, or x4 and x10, or something like that. And so this DNF, in fact, might have many different decision trees computing it, but let's give one particular simple, canonical decision tree, maybe not the best one, but some decision tree which computes this DNF. And we'll just do it in the most straightforward way. We'll kind of query all the variables in the first clause and see what happens. So we'll build this decision tree. Query x1 and then x2. And then we won't do anything smart, just consider all the possibilities, and then x7. Okay, and having queried all the variables in the first term, we'll sit back and take stock. Now, one thing we can notice with this term, there's always some path down the decision tree, particularly the path where x1 is false, sorry, where x1 is true, and then x2 is also true, and then x7 is false. This path is the path that satisfies the first term. Okay, so if you follow that path, you get to a 1, because at this point the first term is made true. We can just stop the whole decision tree and output 1, because the DNF is a big OR. Okay, so that's one special path of depth 3, at which point you can stop the decision tree. Otherwise, we'll just keep going with the next term. So we'll just query. We have x3, x2, and x5. So we'll query x3 here. And actually x2 we don't have to query because it's already been queried, so we don't actually have to query it, so we can skip it. And then we'll query x5 everywhere here. Okay, and again, what we find is at this point, there'll be some path, let's say once we get to this part of the tree, if we haven't already hit this leaf, there'll be some path which again, ends the story, that makes this second term true and lets us output a 1. So that's, I guess in this case, where x3 is 1. And when we're on leftmost branches, where x2 is 0, and when x5 is 1. So x3 is 1, and we're on a leftmost branch because x2 is 0, and x5 is 1. So in this subtree here, let me fill in the x5. When it's 1, we can again stop the tree and output a 1. Okay, and we can do that on all these subtrees we put here. So what I'm trying to say is that for all these next subtrees, there'll be some path at which point we've made the second term 1 and we can stop the tree. Okay, and again, if we don't hit that path, then we just move on to the next term. The query is x4 and x10, so we'll put like little trees on here, everywhere down here. Okay, and these next trees will again have the property that there'll be some path in them of depth 2 that makes the and true, so we can stop. Okay, and we just keep doing this whole thing for all the terms, and this will build some kind of decision tree that computes the same thing as this DNF. And the main thing that I want to state here is that such a decision tree has the property that it is W-clipped. Okay, so this is a term I'm defining. It looks like chipped. Let me try to write it again. Clipped. Okay, so this is a term that PRST defined. What that means is at every internal node, there is a leaf at distance at most W. Okay, so this is the definition of a W-clipped decision tree. I'm not sure why they called it W-clipped. I'm not 100% sure what that means. Perhaps they should have called it like W-escape hatch decision tree, because it has the property that like wherever you are in the decision tree, there's always some escape hatch that'll get you to a leaf at distance at most W. So some sequence of, W steps down the tree that if you magically or luckily take them, you'll get to a leaf. Okay, so that's a W-clipped decision tree. And every, what we've seen here is that every width at most W DNF or CNF, it's the same thing, has an equivalent W-clipped decision tree. Okay, in fact, the class of W-clipped decision trees is broader than the class of width W CNFs and DNFs, but it includes it. And the PRST switching lemma is for exactly this class, W-clipped decision trees. Okay, so in fact I can state it. Here's their theorem. Let phi be a W-clipped decision tree. Then, again, as usual, for all parameters h, a natural number, if we choose a random restriction with star probability epsilon, and we look at phi restricted by that random restriction, and we ask, okay, what's the chance that this restricted W-clipped decision tree still needs a height, at least h? Well, it's exponentially small in h, and with this parameter, as I said, that's something like epsilon times 2 to the w. Now, let me just, for simplicity, write a constant times epsilon times w times 2 to the w. Throw the w in there for correctness. It's basically like 2 to the w to the power of h. Okay, and that's the PRS switching theorem or switching lemma PRST switching lemma that we're going to talk about. In fact, if you're a little bit careful, this constant can be 2. And maybe what I'll actually prove is this statement with this constant being 2 times e. And I think I also need to put like a factor of 3 out here or something. But the constants are not big deals here. Okay, so that's the theorem we want to prove. And quite interestingly, we've made a lot of progress on it already. So the warm-up switching lemma that we did before, just switching decision trees to decision trees, almost gets us a lot of the way there. So let's scroll back up and take a look at that decision tree switching lemma proof. There it was. Took a decision tree of just pure depth w, certainly that's W-clipped, but in a very special way. And then we have this probability that it doesn't get crushed into the random restriction is very small, something like 2 epsilon w to the h. Now, for the PRST full switching lemma, we're just going to start repeating this proof. So, I mean, we'll just put check marks here. Same thing, if the decision tree depth of the restricted W-clipped decision tree is at least h, then that means it has at least one path of length at least h. So if we pick a random path in the restricted decision tree, we have at least a 2 to the minus h chance of hitting it. So that's still fine. Okay, so the probability that the decision tree under the random restriction still needs depth h is at most the probability under the random restriction that this event occurs. Okay, let me not rehash all this. So we used Markov again, and we got down here, and then we did this argument about replacing the random restriction followed by a random path with instead just taking a random path in the original tree and then putting in stars, probably epsilon, and looking at the probability that the number of stars is at least h. Okay, so I want to get back to exactly this point, which I marked with a star. The probability that we're trying to bound is bounded by this, 2 to the h, times the probability when q is a random path in the original phi, that a binomial random variable with length of q trials and parameter epsilon is at least h. Okay, so in fact, let me just copy that down here. Okay, so I'll write proof. As before, the probability is at most 2 to the h times the probability when q is a random path in the original tree, it's W-clipped decision tree, that a binomial random variable with length of q or number of variables in q trials and parameter epsilon is at least h. Okay, so it's the exact same thing as before. And in fact, let me just use, let me use the same union bound as before. Keep my 2 to the h here. And we'll say, look, I mean, in order for this binomial to be at least h, then out of the q possibilities, there must be some h of them where we got all stars, so the probability of that is epsilon to the h. So this is an upper bound as before. Oops, I should add an expectation here. Where again, the expectation is over Q, a random path in phi. Okay, that's just because this probability is bounded by this quantity, by union bound. And again, I'll do the exact same thing as before. I'll use that Q choose h is at most Q to the h divided by h factorial. Okay, so pretty much exactly the same as before. This is at most 2 epsilon to the h over h factorial times the expected value, again when Q is a random path, of length of Q to the h. Okay, and in fact, this is exactly where we were last time when we just had a random switching lemma for just plain decision trees of depth at most w. And then we just said, well, Q is at most w, so we get w to the h here, and now we're done. 2 epsilon w to the h over h factorial. All right, but now finally we're going to do something different because Q is not, in this case, a depth w decision tree. It's merely a w-clipped decision tree. Okay, so it's not that, like in this decision tree, every path down the tree has depth at most w. No, it's merely that for any point in the tree, there is some path of depth at most w that takes you to a leaf. But if you don't hit that path, well, you could keep going. Okay, but no matter where you are, you always have an escape hatch, some path of length at most w that gets you to a leaf. Okay, and now actually we just have a little bit of a probability exercise to bound this expectation. And we can do it rather simply as follows. So let's take a look at this random variable length of Q, where Q is a random path down this w-clipped decision tree. And notice that I want to say that the length of Q is sort of dominated, stochastically dominated, if you will, by a simpler random variable. You see, imagine you're choosing this random path down the tree and you're at some variable, some internal node. We know at this point there is some sequence of at most w coin flips you could take, random choices for how to proceed down the path. So coin flips you could take, such that if you hit those exact right, left-right steps, at most w of them in a row, you would get to a leaf, and then you could stop. So we can kind of imagine that every time when you're constructing this path Q, if you do the perfect succession of at most w coin flips, the length of the path stops growing. And therefore, we can bound the length of Q, or say it's dominated by a related random variable. This random variable, w times g, where g is a geometric random variable with parameter 2 to the minus w. Okay, so remember, a geometric random variable with a given parameter p is like the number of p-wise coin flips it takes you in order to hit a heads. And the experiment we're kind of imagining here is that every time you're at an internal node, we know there's some sequence of at most w coin flips, maybe all heads, let's say, that if you hit that, you can stop. And so we'll just, say, you know what, I'm going to see if I exactly hit that sequence of coin flips. That occurs with probability 2 to the minus w. And if that sequence does hit, then I'll pay, w for making those coin flips, and I get to stop. Otherwise, I'll just retry. I'll have gone, w steps, or maybe at most w steps, and then I'll retry. I'll get to some other internal node, and I'll see if I hit the perfect sequence of at most w coin flips that gets me to a leaf. If so, I'll pay w, and I can stop. Otherwise, I'll just say, well, I got somewhere, and I can keep trying. Okay, and it's only worse for you if these sequences have length exactly w. So you can just imagine we always, see if we hit this perfect streak of w steps that takes us to a leaf. And if it does, we pay w, and otherwise we just try again. Okay, so Q in expectation is, sorry, not in expectation, but as a random variable, is sort of dominated by W times a geometric random variable with parameter 2 to the minus W. And let me write P for 2 to the minus W, simply because it's traditional to call the parameter of a geometric random variable P. Okay, so given that, I mean, we can plug that back up into here and say that this is at most, still 2 epsilon to the h over h factorial. Then we have W to the h. And finally, we have the expected value of G to the h, where G is this geometric P random variable, where P is 2 to the minus W. Okay, and now if you're good at probability and good at technical things, then you can just bound this. I mean, it's a geometric random variable. We're looking at its h at the moment. You can do some calculations if you're good at math. Turns out that, in fact, this quantity, by the way, what should we expect it to be? The expected value of G is the reciprocal of P, is 2 to the W. It takes about 2 to the W tries in order to get W heads in a row. And now we're raising it to the power of h. So it's certainly going to be something like maybe 1 over P to the h, maybe times some extra factors. And indeed, if you're good and you're careful, you can actually show that this is at most h factorial over P to the h. Okay, that's just a general fact about geometric random variables. This is true for any non-negative integer h. The hth moment of g is at most h factorial over P to the h. And so if you accept that, then this whole bound is, well, we can cancel the h factorials like this, and we, P, remember, is 2 to W, and we exactly get 2 epsilon W, 2 to the W, all to the h, as I initially claimed up here we could get. Yeah, so that's actually it. But let me show you like a cheap way, like a non-sophisticated way to get like a slightly worse bound on the expected value of g to the h. That will give us a slightly worse final bound, but we don't have to appeal to some unknown fact about geometric random variables. Okay, so let me just say we're basically done at this point. But yeah, let's just work a little bit on geometric random variables. So, good. How can I bound the expected value of g to the h being at most something where g is geometric with parameter p? Here's a simple way to do it. I can just imagine different ranges that g might fall into. So g might take a value between 1 and I'm going to carefully use the following ranges. H over p. Or it could fall into the range from h over p up to 2h over p. Or it could fall into the range 2h over p up to 3h over p. Okay, you get the point here. Or 3h over p up to 4h over p, etc. And let's see. First, let's compute what's the probability of g being in that range. Well, what's the probability that g is in this range? Let's just say it's at most 1. And remember, g is expected to be 1 over p, so it's not so bad to say that there's at most a probability 1 that it's at most h over p. But now we'll use better bounds over here. So what's the probability that g is between h over p and 2h over p? Well, in order for that to happen, it has to at least be at least h over p, which means that you have to get this. You have to sort of fail at least h over p times. Okay, and the probability of failure is 1 minus p. So in order for this g to be in this range, it has to be at least h over p, and that happens with probability at most. The probability of getting h over p consecutive failures, so 1 minus p to the h over p. And of course, we're going to use that 1 minus p is at most e to the minus p to the h over p. And then we do that because the p's cancel, and this is e to the minus hp. Okay, so similarly, in order to be in this range, well, you have to have at least 2h over p failures. So this is at most 1 minus p to the 2h over p, and using the same trick with e to the power of, this is at most e to the minus p to the power of 2h over p, so e to the minus 2h. Oops, this shouldn't have a p. Right, there's no p here. Just e to the minus h. This is e to the minus 2h. Again here, this is at most 1 minus p to the 3h over p, so that's at most e to the minus p to the 3h over p, which is at most e to the minus 3h. Okay, and the next one's going to be e to the minus 4h, and so forth. Okay, so that's kind of messy looking, sorry about that. That's the probability that g is in each one of these ranges. And then when g is in this range, what is g to the h, what we're trying to bound? Well, in this case, it's at most, we're going to use the topmost guys in the range, it's at most h over p to the h. In this case, it's at most 2h over p to the h. In this case, it's at most 3h over p to the h. At most 4h over p to the h. Okay, and now we just multiply these probabilities times these values and sum. So finally, we conclude that the expected value of g to the h is at most, well, 1 times this, so h over p to the h, plus e to the minus h times 2h over p to the h, plus e to the minus 2h times 3h over p to the h, that was this one, plus e to the minus 3h times 4h over p to the p, oops, this should have been to the h, etc. And again, let's clean this up. Let's see, we can factor out an h over p to the h, and we'll get 1 plus, now let's see, we're going to have 2 over e to the h here. Will I get this right? Yeah, 2 over e to the h, plus 3 over e squared to the h, right, plus 4 over e cubed to the h, plus dot dot dot. Okay, good. And you see this succession of numbers is going down super quick, so it's basically like a geometric series. You know, I mean, the denominator here is going up like powers of e. Granted, the numerator is going up like 2, 3, 4, but that's easily overwhelmed. Plus, we've even got to the power of h. So, like, even if h is 1, even if h is 1, it's, you know, at most this. And this is basically like a geometric series. It's converging. And according to my calculations, this is like e over e minus 1 squared. Anyway, it's like at most like 2.51 or something. Let's say it's at most 3. Anyway, it's, you know, it's basically 1, to be honest, especially if h is large. We'll call this 3 times h over p to the h. Okay, and that's great. Right, so we just have to put this, let's go back to where we were, together with this, we had all these factors, 2 epsilon to the h, w to the h, over h factorial. Okay, so let's put it all together. So therefore, the final probability bound is, let's see, what do we have? 2 epsilon w to the h over h factorial. Okay, times this thing that we just cooked up, which is 3, never mind about that, h over p. Now remember, p was 2 to the minus w to the h. Okay, good, so we can put that together and get this 3, which never mind about, and 2 epsilon w, 2 to the w to the h, and what's left over is h to the h over h factorial. I guess h factorial is at least h over e to the h. So if we plug that in, this is at most 3, again, never mind. And here we're going to pick up another factor of e to the h, so whatever, 2e, that's our constant, times epsilon, times w, times the main thing, which is 2 to the w, all to the power of h. Okay, and that's the end of the PRST switching lemma, which, just to recap, it's a bit worse than the Hostad switching lemma because instead of having constant epsilon w to the power of h, it has constant epsilon and basically 2 to the w to the power of h. That's good enough to get some super polynomial ACC0 circuit lower bounds. And in fact, this turns out it's basically sharp for this broader class of w-clipped decision trees, which, as I mentioned before, is a broader class than with w CNFs and with w DNFs.